Hi folks, this is video tutorial number 19 in a playlist which is devoted to motion design in 3D experience. Uh, it's going to be a very simple problem, a kind of elementary problem that you do in a second year dynamics class. Suppose you have a bowling ball and you throw it on the track, and initially, in all likelihood, uh, the ball will slide, and at some point it starts rolling. I'm sure you have seen this thing in bowling alleys. Now, what I'm going to do is assume that the initial velocity is given by this number, 1 meter per second, and the coefficient of friction between the surface and the ball is a 0.05. The ball is made out of steel. It's a very heavy ball, and the density of steel is given here, and the radius of the ball is 10 centimeter. Okay. Based on that, the mass of the ball comes out to be around 32 kilogram, and the mass moment of inertia, because that's going to come into the calculation, is going to be 0.13 kilogram meter square. Uh, now, let me get the equation. Let me do the problem analytically for you. It's a simple problem. So we're going to use Euler's first law, which is also Newton's second law, Euler's second law, and rolling condition. As far as Euler's first law is concerned, sum of all the forces is equal to mass times acceleration, and the only force that's acting in the horizontal direction is friction force, negative friction force. You can see that. And out of that, you can get the acceleration. And once you have a constant acceleration, this is a constant acceleration, the velocity will drop linearly, as you can see here. Now, when you go to the Euler's second law, we're going to choose the mass center as the reference point. So sum of all the moments about the mass center is equal to I times alpha, basically. Mass moment of inertia to angular acceleration. Now for a sphere, this is what you got for I, and you just plug it in, and notice that here you can solve for omega dot. And assuming the initial condition is initial angular velocity is 0 when you throw the bowling ball, usually you don't have it unless you do give it a rotational motion. We assume that the initial angular velocity is 0, so therefore this can be integrated, and in fact it's also going to be linear. Now once I put the I and plug it in, this is going to clean up like that. Now rolling starts when the angular velocity of the ball is related to the linear velocity of the ball according to this, or omega equal to v. Okay, so what we want to know, we have three equations here involving three unknowns: the time t star at which this happens, and omega t star and via t star. So you can solve for this in basic algebra. You're going to get this information. Okay, now this is going to be the time, this is the velocity when the rolling begins, etc., and it's the angular velocity when the rolling begins. Now for the data that I provided for you, we're going to get the time that it begins to roll is roughly half a second, and at that instant the velocity is 0.71 meter per second, and the angular velocity is 5.1 rad per second. So we're going to be comparing our results against these numbers in 3D experience. Okay, let me go out here, and I'm going to start assembly design. Okay, insert our first part is going to be the ball. Insert 3D part. Okay, I'm going to call this thing ball. And there's the instance name, ball. And we're going to make the color of it orange. Okay, and let's make it. Double click to go into part design. On that vertical plane, I will sketch half a circle, and then I'm going to shaft it to get the full ball. So I'll do an arc. There we are, and let's give it a dimension. The radius of this is 0.1. Okay, and then we exit and pad it no, shafted, shaft this about that vertical axis, and there we are. So this is going to be our ball. Now we go all the way to the top, insert the second piece, which is going to be the track, insert the second piece. Let me call this thing track, properties, track, and track, and make the color of it yellow. All right. The easiest way for me to either draw a rectangle here and then path it properly, or make a plane about exactly 0.1 meter down below, and then draw on it the track. That's what I'm going to do. So let's go in the track, part design, create a plane, offset from this in the other direction, and I'll make it 0.1 there. And on it, I will draw my track. So let me see for a second. Track rectangle. So I'll make it like this. Okay, and I dimension this edge to be 1.5 meter. 1.5 meter. I just want this. Yeah, that's fine. Right there. Actually, let me make it maybe 1.7. What did I do here? Did I do 17? Okay. Yeah, that's fine. Fine. So exit, and then I'm going to pat this thing in the opposite direction, so that is tangent. Actually, there, now it's tangent. Okay, so wow, a ball tangent to that track, you can see that. The width of this, the height of this is irrelevant, doesn't come into the picture. To go all the way to the top, first of all, don't forget to save. Always a good idea to do this. Now, as far as making the model, that's all. But don't worry, also fix this track, because the track is not going to go anywhere. Fix the track. Good. And by the way, I'm going to hide all these planes because I don't need them. Hide them and hide them. Okay, good. And this plane also I don't need. Now we're going to go to motion design. So we go to motion design. What CATIA does immediately, it creates a mechanism for me. You can see that. This thing on the side here. Analysis case, new mechanism. I don't have anything else. And then we say OK. So a mechanism has been created for me. And it's a dynamic step. It's always by default dynamic, unless you change it. Now you go to the global branch here. If you double click on gravity, you see that already automatically it puts a gravity acting downward. You can see that. And this is the number. Fine. You can buy that. And also, if you go to the bodies, there is two bodies. These two, I created them, the ball and the track. And the ground is automatically created in the program. Okay, so if I double click on the ball, notice that I didn't specify what it was made of, but what it does, it takes the density of a steel, takes the density of steel and uses the dimension, you get 32.4. This is exactly what I had here, 32.54, okay? And it also does the I for you, 0.13, right? See, 0.13 because it's, same value in all directions. So that's okay. Now, as far as the track goes, it's really irrelevant. It also uses steel, but it's totally irrelevant because it's going to be stationary. It's not going to go in. And if you don't like it, you can like make it rigid massless, but that's okay. I leave it the way it is. Now, as far as the dynamic step is concerned, it's dynamic step 5 seconds. I'm going to change that thing maybe to 2 seconds, and then we say okay. Because if you put 5 seconds, it's going to fall off this this track. Now, over here, I have to create the interaction between the friction interaction between these two parts. So we go to mechanism, scroll all the way down. Here is where's the friction? We have to find the friction. 3D contact. 3D contact is going to be between the ball and the track. And if you click on the contact properties, I'm going to use 0.05 for friction coefficient. Oh, no, that's the restitution. That's okay, cancel that. Leave that thing the way it is. Let me try it again. I select this and that, and contact properties. I don't have to worry about coefficient of restitution because this thing doesn't hit anything, but the coefficient of friction, sliding friction coefficient is 0.05, as I mentioned in the slide. And don't worry about this. You know what? What I'm going to do is let me go ahead and it really doesn't matter, but I'll make this thing 0. Okay, stiffness scaling, make it 0. That's okay. That's doesn't even with that value, you're going to come up with numbers which are relatively close. Now I don't have any joints. I don't have any joints, and that's pretty much it. Oh, initial condition. You have to specify initial condition. Now there's an icon here, initial condition. You click on it. It says, do you want to apply it on a joint or the marker? I don't have any joints anyways, so I'm going to say marker, and I'm going to select the marker from the select this thing from the tree. Here's the ball right there, the marker right there. Or if you, because the markers are not showing on the screen, if you wanted to see them on the screen, you click on the, in this visualization, there is a marker. Where is the marker? Right there. You see that? Because I didn't have it on the screen, I took it from the tree. That's okay. So from the tree, and what is it that I want to do? Initial condition, translation. I don't have any rotation. I said the initial velocity, angular velocity is 0. So in the y direction, we specify velocity in the y direction, and you're told that it is 1. Okay, in the y direction, 1 meter per second. You say okay. That's pretty much it. So I go to the simulation, and I'm gonna run it. Hopefully I didn't forget anything. Run. Just give it a few seconds. Okay. Oh, it's failed. What was it missing? Something is missing here. Let me check the message here. Messages. See what is it that didn't work. Okay. That let me go ahead and put that thing. Let me go ahead and put that stiffness back to something that's not 0. I'll put down what it was by default. Now we're going to go run it. Yeah. Wow. Okay, succeeded. Close. Now we're going to go and check, select the result, dynamic step, results, and let's animate it. Okay, okay, so that's good because almost falling off. So actually you can see this. Either I could have made the time shorter or could have made this thing longer. But anyway, so that's good. Now let's go and plot 2D plot. What is it that we want? Okay, so let's see. What is it that, oops, what is it that we want? Well, we want the sphere bodies. Move this thing on the side so that you can see it better. We want bodies, and what do we want? Ball. I want the linear velocity in the direction y, velocity in direction 1, y, and angular velocity about the about the x-axis. This is the x-axis. So add these two to the plot. Look at what happened. Let me make this thing a little bit bigger to show you what's going on. Notice that around 0.55, this is when the sliding takes place. Around 0.55, suddenly things change. This is when the rolling starts. So 0.55, the break point for both of these. One of them is this is the angular velocity, and this is the linear velocity. Linear velocity, you can see that around 0.55-ish, something happens. So that is the time. That is the time of 0.55, 0.56, something of that ballpark. Now, what about the magnitude of the velocity at that breakpoint? Should be around 0.71 meter per second. So let's go back here. So this is the linear velocity. Let me hide this thing for you. Okay. So here's 0.55, 0.5. Yeah, something around that. It's around 0.7, right? Points, you can see that. Just read this thing, 0.7. So that's pretty much what it is, 0.7. And the angular velocity, let's go ahead and check that. Angular velocity, let me get it. I don't want linear one, I want the angular one. And it's around 7. That's around 7, not 5. Now, one thing I'm going to do before I stop this, so basically, we got the theoretical result. But one thing I'm going to do, let me say okay here. I'm going to go and change that stiffness to see. Remember contact? I made the 0, it crashed. Let me make this thing a small number. See what happens, whether it has an effect. 10 times smaller, and we're going to run. So we go to simulate, run, wait until this thing finishes, and then we're going to check the plot there. You say close. Didn't make that much of a difference. You can see that it's still 7. This is supposed to be 5, but yeah, we're not getting the theoretical result for angular velocity. It's not bad, but it's not 7. Ours is 5, 5-ish. Okay. All right, that's pretty much it. Good luck.